Hello guys, it's Digitronics Nepali here again, and today we are gonna look at the different ways of designing the algorithm. We are gonna explore the different architectures, and we are gonna specifically focus on pipelining, different ways of pipelining, multi-stages of pipelining. So let's get started. So why do we need pipelining? So let's look at this example. Here is a combination logic. Here are two resistors, and this is clock signal. So if we keep a combination logic simply like this, so then there is a long delay between this and this. So there is a propagation delay when the data flows from this place to this wire. So due to that propagation delay, we will not be able to clock this clock at very high frequency, because the clock will reach from this place to this place instantly, but the data will not reach from this place to this place instantly, and it takes time. So we won't be able to clock very high with this type of architecture. So to get over this, we can use this sort of architecture where there is a register or flip-flop between the two combinational logic. When there is a register, then it stores the data from here. Through this architecture, we can increase the frequency, of course. Also, we can give the new data in every clock cycle, and the data will be taking data every clock cycle, and that data will be stored here, and in next cycle that data will be transferred to here, and so we can increase the throughput. So this is the best way of implementing the high throughput architecture. So let's look at how specifically we can achieve that. First of all, let's explore some of the other design, and we'll look at the pipeline design. So this is basic iterative architecture. We just give input here, and here is a register, and here is a round, and it can be round of any as function or any algorithm. So first of all, this line will be selected, and it will pass through the round, and the output of round will be fed to the input again through the register. And this is basic iterative architecture, and this will occupy the minimum amount of area because it has only one round, and its throughput will also be low, and it will have the worst performance. So let's look at it, the example implementation of it with Keccak. So this is Keccak with basic iterative architecture. If we look at the simulation result, so this is our data in, and here is our start signal, and here we get the ready signal asserted. So when there is ready signal, this is our required output. And only after, the disadvantage of this basic iterative architecture is that only after we get the first output, we will be able to give another output. So after ready signal, we get ready signal, we can give another input, and we can start the assert signal again, and then that will give output here. So this is very slow because we have to wait until the result of first data comes. So this is it has lowest throughput, so it is the worst in terms of performance, but it is also the best in terms of area. Like if we look at the simulation synthesis report, we can see that it is utilizing only 0.3% of VCU1525 board. So this is very low area and worst performance architecture. So if we look at let's look at another architecture that we are focusing on, that is pipeline architecture, fully pipeline and fully unrolled architecture. So what we do here is register, here is round 0, and there is another register, and here is another round, and so there is a register between each round, and it is not repeating itself, it is not iterative. So it is fully unrolled architecture. So here in case of Keccak, there will be 24 rounds. So here will be 24 rounds, and there will be 24 registers in between. So we will be able to give new input every clock cycle, and we will be getting output every clock cycle. And this is best in terms of performance. It has the highest throughput among any architecture, and we can clock up to very high frequency with this architecture. If there is a long propagational path delay in these rounds, then we can simply add one more resistor and we don't have to worry about any timing issue. This is the simplest form, and there will be no timing issue with this sort of architecture. If you want to split the round, we can just put resistor in between and it will just work fine. So let's look at the implementation of it. So this is fully pipeline architecture, and if we look at the simulation, so we are giving input every clock cycle and we are getting output here also every clock cycle. So this is best in terms of throughput. If we look at the design, it's simple. There are resistors and here are round. We keep output of one round is fed into the input of another one, and this is just simple. So this is fully unrolled architecture, and the demerit of this architecture is only one thing, that is area. It consumes a lot of area, and it consumes around 4% area in VCU1525. So this is very hard on area. Otherwise, it has the highest throughput and highest performance, best performance. And so what if there is no area? We want to implement this sort of architecture, a pipeline architecture with very high frequency, very high throughput, but we do not have the area. So there is a trade-off between area and throughput. So if we look at the area, this is the axis of area, and this is the time to calculate something. In case of hashing algorithm or mining algorithm, it's the time to calculate golden N1s. So this means very low hash rate, and this means very high hash rate. So it takes less time to calculate hash, that means. So this is very high hash rate, and this is very low hash rate. This is low area, and this is high. This is very high area. So this is our best performance algorithm, best throughput. It has the best throughput, and this is the worst in terms of performance. It has the worst throughput. Also, it occupies less area. So these are two extreme of this basic iterative architecture and fully unrolled architecture. So the job of the designer is to able to fit the area in the required FPGA. So if the area of device is less than the required area of the given throughput, then that will be problem. So that is the problem if we have less area. So our job is to find the position in this between, where we can manage the throughput, where we can trade off between area and throughput. So this is feasible solution. We can make design anywhere here, but we cannot make design anywhere here, because that will be equivalent to as high throughput in less area, and that's not possible. So our job as a designer is to make our design as closely as this line as possible. So if we can make up to near to this line, then that will be our best design. So to make that design, there is another architecture that we are going to discuss. This is pipeline architecture with not fully unrolling, but maybe half unrolling or 1/4 unrolling, and this is that sort of architecture. What we have here is, in this case there are two pipeline stages. Here are two rounds, and so two pipeline stages, and there is resistor in between. So this is better in terms of performance with respect to basic iterative architecture, but not as good as fully unrolled architecture in terms of performance. So this is two pipeline stages architecture. and I'll show you like with 12 pipeline 12 architecture with 12 pipeline stages. So let's look at it. So here is our architecture with 12 pipeline stages. So this is same Keccak, like fully unrolled, but it has got only 12 rounds. So we will be able to give input every 2 clock cycle instead of 1, and its area will also be half. If we can get half, if we can get half the throughput with half the area, that's a very good design. That's great. So it's occupying only 2% area, and if we look at the simulation result, so here is our simulation result. We can see we can give input every 2 clock cycle, and we are getting output every 2 clock cycle. And so this in this way we will be able to fit the algorithm, any algorithm in the FPGA with required area, and we'll be getting the throughput correspondingly. So these are the different way of implementing the algorithm. Thank you, and in next video we will see how we can get this unroll up to half, how we can make this architecture half unroll. So it is not as simple as just placing the 12 algorithms simultaneously. There are lots of other design consideration also, and we'll look into those design consideration in the next video. Thank you.